Hello and welcome to the Algebra 2 Test 8 study guide covering probability and statistics. My name is Mr. Sipple and I'll be walking you through 10 problems that match up with almost exactly to the 10 problems that you'll find on the retake test. Glad that you're here, glad you made the decision to do something about your grade, to raise your grade, right? So you're not here because you're in trouble, you did anything wrong. The whole point here is that we're just trying to reteach the material to you, or maybe, and in some cases, maybe you never even learned it the first time around. Well, that's all right. Either way, we'll make sure that you know how to do the stuff, and so then that way when you retake the test, you'll be golden. You'll get an A, and then we'll see your grade go up. So let's just start with putting your name on your paper, of course. I want to make sure we know who you are. And if you are coming from a different teacher other than myself, if you'll put your teacher's name. And just real quickly, if this is your first time with us, the format of the way that the video and the study guide goes is you'll notice that there's 3 columns across the page. So what I will do is I will do the column or the problem out of the first column as an example to show you how to do it, and then to give you practice, right, because that's the only way that you're going to get better at this and make sure it sticks in your mind, is that if you get some practice at it. So the middle column and then the problem on the right side is an opportunity for you to practice the one I just showed you. Now what I'll do is I'll show you the answers to the middle column and the one on the right, but I won't show you how to work it out. So that's where you'll have to do that on your own. What you want to try to do is to make this as beneficial to you as possible. Is you want to try to do as much of this on your own as you can. If you're just kind of just staring at the screen and zoning out and copying down whatever I'm writing, you're not going to get a whole lot out of it. So the more you try to do this on your own, the better it will be for you. All right, well, let's go ahead and get started. All right, so taking a look at the first question. So how many different sundaes could you make if you had a choice of 12 different ice creams, 3 different kinds of cones, and let's say you had a choice of 8 different kinds of toppings? So what you have to think about on this one is you have to think about how many different ways could you come up with, you know, given those 3 different choices that you're going to have to make, or 3 different decisions you're going to have to make, how many different possibilities could you come up with? Well, I think the first thing that you ask yourself is that you ask yourself, well, how many different decisions do I have to make? You know, and kind of put yourself into the problem. You know, if you're walking into Yogurtland or, you know, I don't know, whatever ice cream shop, right? But you know, you're having to make kind of a choice of what you want. So there's really 3 different decisions that you have to make. Right? Maybe we'll highlight that. You have to first of all decide what kind of ice cream you want. Then you have to decide what kind of cone you want, because maybe they got like a waffle cone, or maybe you get a cup or sugar cone, or who knows. And then there's 8 different toppings, right? So those are really your 3 different decisions that you have to make. Is that you have to decide what kind of ice cream do you want, and then you have to then decide what kind of cone do you want, and then the final decision is on toppings. Now, what I'm showing you, how we're going to set this up is referred to as the fundamental counting principle. It just basically says that if you take the number of decisions that you have to make, and then you figure out how many choices that you have for each one of those decisions, that you could find the number of different ways that you could come up with a combination just by multiplying those 2 things together. Move this around a little bit. So again, our 3 decisions were what kind of ice cream, what kind of cone, and what kind of toppings. And then we go through and we ask ourselves, well, how many choices do you have for each decision? Well, if we take a look at it, looks like we have 12 different choices of ice cream. It says we've got 3 different kinds of cone. And then we've got 8 different toppings. So if I wanted to know what those 3 multiplied out, right, and it's actually always multiplying, so we're always just multiplying those things. And I should mention to you, by the way, and I actually forgot to mention it from the very beginning, you'll probably want a calculator for some of this at least. If you don't have your own calculator, either because your own calculator, say through your phone, I'll show you a calculator that you can use, that you can pull up. If you just open up another web browser and then you Google scientific calculator, And Google's got their own, but I actually like the first one down. If you'll click on the first link, it'll actually pull that calculator up. And you can minimize it. You can change the size of it so it's not all in the way. So maybe kind of move that out of the way a little bit. But because we're going to use this calculator for a couple different things as we go throughout this study guide. All right. So 12 times 3 times 8. So let's multiply that out, right? 12 times 3 times 8, which gives us 288. So there's a total of 288 different Sundays that we could come up with. Right. And this is really the kind of the shortcut way of doing it. You may have seen something like this in middle school where you did a tree diagram, which is another way that you could solve this, but the problem is it ends up being a lot of work. Because, so for instance, let's say I say the first flavor is chocolate, right? And then I say, well, I've got a choice of 3 different kinds of cones. Maybe I do waffle, maybe I do sugar cone, maybe I do it actually as a cup. And then you say for each cone, then there's a choice of 8 different toppings. 5, 6, 7, 8, right? And then I would do that for each one of those. And that's actually just only for one choice of ice cream. So you could see how that would really kind of be a pain to do it out that way. So, I mean, you can use a tree diagram, but we're going to actually use the fundamental counting principle to come up with the answer for us here. All right, so go ahead and pause the video, try 1.2 in the middle and 1.3 on the right side. All right, so let's see what you came up with. For 1.2, the problem in the middle should have got 216 different combo meals. And for 1.3 on the right side, should have got 350 different outfits. So if you didn't get either one of those correct, pause the video, go back and see if you can figure out what your mistake was. If you're not able to figure out where you went wrong, then ask me, right? So that's one of the reasons why I'm in the room here with you, is that don't think that you have to count just on the video. If you're still not sure about something, then just ask. All right, so let's go ahead and take a look at the second question. Right? Now, you don't have to write this down. I just wanted to point out 2 things to you, maybe pieces of vocabulary. What we're going to talk about is something called a permutation and a combination. So a permutation is an arrangement where the order does matter. Okay, so let's say, for instance, if order matters. So let's take, for instance, this lock, right? If your combination to this lock is 16, 31, 13, and you don't put it in the right order, it's not going to work. So there's certain issues or certain cases where the order does matter. So a telephone number, right? If you don't put the telephone number in the right order, you're not going to get the right person. A password to a website, right? So these are all cases where the order does matter. Now, sometimes you can rearrange things in where the order does not matter. So an example that I'll use on that, for instance, is a pizza. Is that then when you call up to order a pizza, it doesn't really matter how you tell the guy you want the pizza. As far as the way that you order the ingredients, you're going to get the same pizza either way. So that's an example where the order does not matter. Also, the lottery, right? When you pick the lottery numbers, you just have to match the correct lottery numbers. You don't actually have to get it in the order that the ping pong balls come out of the machine. So the order doesn't matter there as long as the numbers match up. So sometimes order matters, sometimes order does not matter. It can be a little bit tricky to tell the difference between order when order does or does not matter, but that's one thing that we'll discuss throughout this study guide. All right, so let's look at 2.1. So this is an example of a permutation. A password is a permutation because the order matters, right? So I'm just going to make a little bit of a note here, is that this is an example of a permutation. So a password, for instance, is a permutation because the order matters. And again, if you ask yourself, well, why does the order matter? Well, take any password that you have to any website. If you don't put the password in the correct order, it's not going to work. So that's what we mean by order matters. Now, so in this situation, this person wants to come up, see how many different kind of passwords that they can come up with. So she just wants to use 3 letters in her name, Eva, and followed by her birth date, or when she was born, 1982. So we want to figure out, so for instance, Eva 1982 or Eva 8219, right? So we're trying to figure out how many different ways could you mix those up. Well, so when it comes to the letters, and so again, this is where you have to say how many decisions do you have to make. Well, you have 7 decisions to make because the password is 7 characters long. 3 letters, 4 numbers. So 1, 2, 3, 4, 5, 6, 7. Now, so there's 3 letters that she's using, and I'll just do, let's say L for letter. And then there's 4 numbers that she's using. All right. And then what we want to say is how many different, possible arrangements could she come up with? Well, there's 3 letters in her name, E-V-A. So E, V, and A. So if I said, well, how many letters could I put right here? Well, I could put an E, I could put a V, or I could put an A. So in that case, then what I could say is that this would be 3. But then once I pick one of those letters, so let's say I decide that I want this to be an A. Now, for this spot, I only have 2 letters to pick from. And then let's say I want it to be an E next. Well, now I only have 1 letter to pick from. Right, so that's how many different choices I have. Let's talk about the numbers, for instance. Right, so if the numbers, in this case, 1982. So I start from the same thing. How many numbers do I have to choose from? Well, 1, 2, 3, and 4. And then I say, okay, well, let's say I want the first number to be a 9. And then I say, well, how many do I have left? 1, 2, 3. So I got 3 to pick from. Say I want the next number to be a 2. Well, now I've got 2 to pick from. And now I've only got 1. And then so that's what we end up with. Right? And we'll talk about the notation a little bit more into the next problem. But what this is referred to when you see this 3, 2, 1, we referred that to as 3 factorial. That's kind of a shortcut way to write it. So factorial is just a multiplication countdown. So for instance, that would be 4 factorial. We'll talk about factorials a little bit more in the next problem, but just want to introduce that to you because that's one way you could write that. Otherwise, right, so you're just going to multiply all that out. So, and the reason why I say the factorial notation is because calculators have that button in there. So instead of, let's go back to my calculator here. So I can see I could just type in 3 factorial and 4 factorial. And, oh, well, it didn't like that, did it? Let's try 3 factorial times 4 factorial. Okay, I liked it that time. Different calculators are different, so you have to kind of understand the specific language that each calculator speaks. So this one just wanted a times in between the two. So there's 144 different passwords we could come up with. Now, if you're not sure, yet, at least what I just did with the factorial, well, then you could just type in the numbers, right? So you could do, what I did there was I just did 3 times 2 times 1 times 4 times 3 times 2 times 1. And we get the same answer. But so hopefully you could see where, it wasn't too bad to type that in, but let's say it was 100 factorial. Well, you wouldn't want to type all that in, so that's why that button's there to make your life a little bit easier. All right, so go ahead and pause now and try the one in the middle and try the one on the right side. All right, so let's see what you got. For 2.2 in the middle, should have got 240 different passwords. And for number 2.3 on the right side, should have got 144 passwords. Just a coincidence that that happens to be the same answer to 2.1. So just a coincidence there. All right, so again, if you're not sure, where you went wrong, see if you can figure it out on your own. If not, ask. Otherwise, we will move on. All right, so let's look at now, question number 3 gets into looking at a combination. So we just said a permutation is where order matters, right? A password, the order matters. If you don't type it in the right order, it won't work. But what we're going to look at now is a situation where order does not matter. Where order does not matter. And so again, our example there is the pizza. Another example would be what you see with this problem. So 3.1 says you have 5 friends, but you can only pick 2 to go with you to a birthday party. How many possible choices do you have? Okay. Now, I think just so you get a little bit of an understanding on this one, I'm actually going to kind of show you this the long way first, and then I'm going to show you the kind of the short way. So let's say you got 5 friends, right? So let's say Juan, Anna, Cynthia, Marco, and let's pick a 4th friend. Oh, let's say Ben. Alright, so those are your 5 friends. Now this is an example where the order doesn't matter. If I said, hey Mom, you know what, I want Juan and Anna to go with me. And Mom says, alright, well Juan and Anna can go with you, that's fine. And then you say, oh, you know what, Mom, I changed my mind. I want Anna and Juan to go. Mom's going to be a little confused because that's what you just said, right? Those are the same 2 people. So the order doesn't matter. The order that I tell Mom, the 2 people that I want to go with me, the order doesn't matter there. So what you can see, and we can actually, one way to actually solve this problem is by using a little table. So let's see, if I think about all the different pairs that I could come up with, right? So let's say I could invite Juan and Anna. I could invite Juan and Cynthia. I could invite Juan and Marco. Or I can invite Juan and Ben. Now, if I think about all the different, so let's say I want Anna to go, and I think about all the different matchups for Anna. Well, I can invite Ann and Juana, or Anna and Cynthia, Anna and Marco, and Anna and Ben. But the thing is that Juan and Anna Juan, those are the same 2 people, so I can't. That's not a unique or different pair, so I can't count that twice. Let's say if I started with Cynthia. So if I said Cynthia and Juan, and Cynthia and Anna, and then Cynthia and Marco, and Cynthia and Ben. Well, here's the deal again. I've already got Juan and Cynthia right here, so I can't count that. And then Anna and Cynthia, I can't count that. And let me go with Marco now. So Marco and Juan, and Marco and Anna, Marco, Cynthia. Hopefully you see there's a little pattern developing. And Marco and Ben. Well, so again, I can't count something twice. I've already got Juan and Marco right here. I've already got Anna and Marco, so I can't count that. And I've already got Cynthia and Marco, so I can't count that either. And then if we look at Ben, so I could say Ben and Juan, or Ben and Anna, or Ben and Cynthia, or Ben and Marco. Now, for this last one, you'll see that I've already counted actually all of these. All of those are repeats. So the only ones that are unique, the only ones that don't repeat, you see it's almost this kind of triangle that emerges, would be these right here. So how many different ways could I come up with that? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a total of 10 different possibilities that I could come up with here. So we could say there's 10 different pairs of people. Okay. Now that's kind of the long way of doing it, right? So I say that's kind of the long way because we had to write out all this table. Wasn't too bad because there's only 5 people, but let's say you're talking about a wedding, some large event, and there's hundreds of people, thousands of people. Well, you wouldn't want to do it this way. So let me show you the shortcut. Let me show you the shortcut on this one. So I'm just going to move this out of the way momentarily. And let me show you the shortcut. So the shortcut is this formula that you see over on the bottom right-hand corner, and it's actually the formula that's listed on the top of your page there. And the way this works is that it's using factorials, which again, a factorial is just the multiplication countdown. So for instance, like an example would be 4 factorial, which would be 4 times 3 times 2 times 1. And what this is that the n represents the total, and I'm just going to make a couple notes on this, and you may want to do this on the top of your page. So the n represents the total, and then the r represents what you pick, and then what you don't pick. So what I mean by this is that, for instance, in our situation here, we have 5 friends, but we can only choose 2 of those friends. So the way that you would interpret this is that from 5, we're going to choose 2. Right? That's how many that we're picking. From 5, we're going to pick 2. And so the notation, the way that this gets written, is the total goes on top. So for instance, a total would be 5 factorial on the top. And then what we pick, which we're picking 2 people. And then what you don't pick. Well, so that means there's 3 people that aren't getting picked. Now, the way that you write this out, again, 5 factorial means 5 times 4 times 3 times 2 times 1. And then 3 factorial means 3 times 2 times 1. And then 2 factorial means 2 times 1. Now, so what I can do is that I can cancel the 3's, I can cancel the 2's, I can cancel the 1's. I could say 2 goes into 4 2 times. And then I look at everything that's left over. So what I've got left over is I've got left over 5 times 2. Well, 5 times 2 would be equal to 10. So I get exactly the same answer that I got from writing out that table. The only difference is that it was a whole heck of a lot less work and took me a whole lot less time. Right? So I showed you the table because I wanted you to kind of understand the big picture, but this is really how we're using the factorials is how we're going to approach these problems. And it's really kind of how I want you to work them out from here. All right, so go ahead and pause now. Try 3.2 in the middle and then 3.3 on the right side. All right, so let's check in with you. You should have had an opportunity to do both of those problems. 3.2 should have got 220 different combinations of shoes. And 3.3 should have got 70 different pizzas that you could make out of only picking 4 toppings. All right, so let's go ahead and take a look at 4.1. And again, if either one of those you're still not sure with what you're doing, see if you can figure it out, ask before you move on. Right? It's really important that you understand what you're doing before you move on to the next problem. In part because these problems kind of build on themselves. So now what we're going to do in number 4 is really the same thing that we just did. The only difference is that now we're going to do it for kind of 2 different things. We're going to look at kind of 2 different subjects in the problem. All right, so it says there's a total of 8 guys and 6 girls. So let's see, we've got 8 guys and we got 6 girls. But we want to pick a group, right? So like we're going to do like a smaller group. So we're not going to pick all 8 guys to make this group. We actually only want 3 guys. And of the 6 girls, we don't want all 6 of them. We just want 2. Right, so the idea is here is taking a larger group of people and we're saying, okay, we want to make a smaller group. And then the question is, well, how many different ways could we make those groups? Well, so you actually have 2. So this is called a compound combination because you actually have 2 different ways or 2 different things that you have to look at. We have to look at guys, because that's what's one part of the group is going to be made up of. And we have to look at girls, which is the other part of how this group is going to be comprised. So let's see here. So we're going to choose, so from 8, right, because remember the first number always represents the total. So from 8, we're going to choose 3. And then for the girls, there are 6 girls. And so from 6, we're going to choose 2. Right? So, and again here, this is saying from 8, because there's a total of 8 guys, we're going to choose or pick 3. For the girls, there are 6 girls total. So from 6, we're going to choose 2 or pick 2. All right, so what that means is that we're actually going to have 2 different factorials that we're going to have to set up. So let me scroll down here a little bit, give us a little bit of room. So the total always goes on top. So from 8, I'm going to pick 3. So if I pick 3, that means there's 5 guys that don't get picked. And concerning the girls, there's 6 total. Don't want all 6, we just want 2. So if we pick 2, that means there's 4 that we don't pick. All right, and so then from there we just want to be able to simplify that, right? Now I'm going to show you a little bit of a shortcut that I didn't quite show you on the last one when it comes to writing these things out. So let's take 8 factorial. Now 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But what I notice is that if I look at the bottom, there's a 5 factorial on the bottom as well, which would also be 4, 3, 2, 1, 4, 3, 2, 1. So what I can do is I can actually stop there because I know that they'll cancel each other out, so I don't have to write out the whole thing. 3 factorial would be 3 times 2 times 1. And then I can do some canceling here as well. So 3 goes into 6 2 times, 2 goes into 8 4 times, and then I just need to multiply whatever's left over there. And it's not a bad idea to highlight what you have left over, just make sure you don't miss anything. So 4 times 2 would be 8, and then 8 times 7 would be 56. Alright, and now what we're going to do is we're just going to repeat that same thing for the girls. So 6 factorial on top, so 6 times 5 times 4. I look down at the bottom, I see another 4 factorial, so I know that those things will cancel. And then 2 times 1. So doing some canceling here, the 4's cancel. 2 goes into 6 3 times. Taking a look at what I have left over, I've got a 3 and a 5 left over, which would give me 15. Now, all I have to do is just multiply those two things together, 56 times 15, which would give me 840. So 840 different ways that you could pick out of those total, right? How many different ways you could pick those 5 people, right? And there is somewhat of a shortcut. So you'll notice, where I got 56 and where I got 15. I did want to show you one thing on this calculator because it has the ability to do it. Start back at what I did up here on the top. From 8, choose 3. So this calculator, if you look on the left side over here, there's a button that says NCR. So that represents from whatever the total is, you're going to choose whatever amount you're choosing. So the calculator actually has a way of doing all of this work for us. And I just wanted to show you it so that you knew that that was a possibility. On this particular calculator, what it wants you to do is it wants you to hit the button, and then it wants you to tell you the total. So there's a total of 8 guys, comma, just to separate the numbers, but how many you're actually picking. So remember, we were just picking 3. And then it just wants you to then close it off. So you see we got 56. So 56, which is the number that we got right here. Doing the same thing for the girls. So for the girls, there were 6 girls, but we only wanted to choose 2 girls. And we get 15, which is the same number right there. So I want you to be able to do it this way, but I think this is also a good way to check your answer, right? So I want you to know how to do this, because for instance on the CST, you're not going to have the calculator to do that for you. But so you got to know how to do it the old school way, doing it out by hand. But then I think that's a good way to check your answer. All right, well, go ahead and pause now and give 4.2 and 4.3 a chance and see what you get. Alright, so let's check your answers for you. 4.2, you should have got 350 different combinations of cats. And 4.3 on the right side should have got 270 different ways that you could grab 2 pencils and 2 pens from a cup. Alright, so pause if you didn't get either one of those correct. If you did, let's make it to the halfway mark here, right? So number 5. Last question on the front side. Alright, so you got one box contains, ooh, there's a lot of words, right? And I know you're already looking at that and you're like, wow, that's a lot of words. Well, I think the key on any of these kinds of problems is to try to, I don't know, try to simplify it a little bit so where there's just you're not having to read so much. So it says that there's one box that has 6 red and 2 blue, and then there's a second box, right, that has 4 red and 8 blue. So it says if you pick one marble from each bag, what is the probability that they are both blue? So we're looking for the probability that they are both blue. Well, one thing I like to do with these kinds of problems is make a little inventory. So and there's one box, and just draw a picture. So there's a box, and in one of the first box it says there's 6 red, and then there's 2 blue. And so for a total, actually let me make my box a little bigger here. Right, so then that means there's a total of 8 marbles in this first box. Alright, and then let's check out the other box, right? Because they said there's a second box. So in the second box is 4 red and 8 blue. So 4 red and then 8 blue. So for a total of 12 in that box. And then what we're saying is if you reached your hand, and yes, that is a hand. It's a sad-looking hand, but it is a hand. If you reached your hand and grabbed one marble out of this box, and then you grabbed one marble out of that box, what's the probability that they would both be blue? Well, so what happens is that you're looking for the probability of getting a blue out of the first box, probability of getting a blue out of the second box. The little note that I put up here is that the probability of finding 2 different things happening is you got to find the probability of each individual thing happening and then multiply those 2 things together. So the probability of getting a blue out of the first box, well, the probability of that happening is going to be 2 out of 8. And then the probability of getting a blue out of the second box is going to be 8 out of 12, because there's 8 blue out of 12 total. And now what we want to do is we just want to multiply these 2 things together. Well, remember when you multiply fractions, what you can do is you can cross cancel first to make it a little bit easier on you. So, 8s cancel each other out, and then 2 goes into 12 6 times. And then I just multiply straight across. So if I multiply straight across, I would get 1 out of 6. So there is a 1 out of 6 chance that you would get those 2 marbles. Another thing that I like to do, and we'll see this in the next couple questions, is I just like to convert it to a percent. Because when you talk about the weather, for instance, and you say, well, there's a 60% chance it'll rain. Most people don't speak in terms of fractions, right? Most people don't say that there's a 3 out of 5 chance it's going to rain. So what we want to do is just, and for the test itself, the answer actually will be left as a fraction, but I just want you to see, so we'll say approximately 17%. So for the test, it'll be a fraction. You don't have to do this decimal part, but I like converting it to a percent because I think it makes a little more meaning. All right, so pause now and try 5.2, 5.3. All right, let's check those answers for you. 5.2 should have got 2 out of 15, so roughly a 13% chance of grabbing a lime out of each bag. And then for 5.3, should have got 5 out of 12, which is roughly a 42% chance of grabbing a highlighter out of each one of those backpacks. So if you didn't get either one of those correct, go back, correct yourself. If not, we will move on. All right, to the back side. Number 6. So it says, so a container's got some chocolate chip cookies in it. It's got some peanut butter cookies in it. What's the probability the first cookie he eats is chocolate chip, and the second is going to be peanut butter? All right, so I'm going to do kind of the same thing. I'm going to make a little inventory of what we've got. So it says we've got 10. I'm just going to highlight what we've got here. So it says we've got 10 chocolate chip. So 10 chocolate chip. There's 6 peanut butter. And then the question is asking, what is the probability that the first cookie is chocolate chip and then the second is peanut butter? So first cookie, chocolate chip, second peanut butter. Alright, so let's take our inventory. So we've got 10 chocolate chip and we've got 6 peanut butter. Making me hungry. And let's add this up. So that gives us a total of 16 total cookies. Alright, so what we're looking for is what's the probability that the first one will be chocolate chip, we'll just abbreviate CC for chocolate chip, and that the second one will be peanut butter, and we'll do PB for peanut butter here. Alright, well, chocolate chip, well, it looks like for chocolate chip there is 10 out of 16, so that probability would be 10 out of 16. And then for the peanut butter, you're probably thinking, oh, 6 out of 16. Well, here's the deal, though. It's not going to be 6 out of 16. Because, see, what just happened is that we just ate a cookie, right? So now there's one less cookie in the cookie jar. So if you came and, someone already ate a chocolate chip, well, now there's only 9 chocolate chip cookies in the cookie jar. Well, if there's only 9 chocolate chip cookies, that means there's now only 15 total cookies in the cookie jar. So yeah, when the first one comes along, and yeah, there's 10 out of 16. But then once one of those cookies gets eaten, now there's one less. So there's still 6 peanut butter because he didn't have peanut butter, right? So there's still 6 peanut butter, but what's different there is that there's now 15 total, right? And this is an example of an dependent event. The previous example with picking marbles and that sort of thing, it's independent, right? What you grab out of one box doesn't affect what you grab out of the next box because they're 2 separate boxes. If you look at this, however, this is one large container. So on those other examples, we were talking about 2 different boxes, 2 different bags, 2 different backpacks. Here, you're talking about one container. So when you take something out of this one container, now that does affect what's going to happen. So the other, number 5, was an independent event. This is a dependent event because what happens first does impact or affect what's going to happen next. So we're going to do some cross-canceling here. Doesn't matter where you start. 5 goes into 10 2 times, goes into 15 3 times. 6 we can divide by 2. And then we look to see if we can do any other canceling. And you can, when you cross cancel, by the way, you can keep canceling, right? So like the 3's, I can cancel those one more time, and I can say 2 goes into 8 4 times. So if I look at what's left over, it might be a little messy there. Maybe I'll highlight what's left over here. But if I look at what's left over, I've got a 1 left over, and I've got a 4 left over. So that would be 1 out of 4, right? Or 25%. All right, so dependent event. So just know on this problem that the total for the second fraction will be 1 less. All right, so go ahead and pause now and try 6.2 and 6.3. Alright, so let's take a look at 6.2. So kind of a funky fraction on this one. Should have got 30 over 119 works out to being roughly 25% chance of grabbing a scientific and then grabbing a graphing calculator. And 6.3, and just to go say 2, again, why this is dependent is that the teacher's passing out these calculators. So the teacher goes up to one student, gives that kid a calculator, and when the teacher comes over to you, now there's 1 less calculator, right? So that's why it would have been out of 24 for the second. And 6.3, again, same thing. You're lined up for a giveaway. So first person in line, they get something. So assuming you're the second person in line, you walk up there. Now there's 1 less prize because, well, the person in front of you got the first prize. So it should have been 8 out of 33, or roughly 24% chance. Alright, so let's take a look at 7.1. Now, what's different about this is that it's going to be another probability problem, but the difference here is that we're going to be grabbing more than one thing at a time. So that's where it makes the probability more complicated, right? Because if you think back to 5 and 6, whether we were grabbing into one container or two different containers, we were reaching in and only grabbing one thing at a time. But with number 7, we're reaching in, we're actually grabbing multiple things. So that's where it makes the probability a little bit more complicated. So let's take a look at what we're dealing with in the problem. So there's 8 mints and 10 pieces of gum. And then if you randomly take 3 pieces, what is the probability of grabbing 1 mint and 2 sticks of gum? Well, so see, where this is more complicated is because with the 10 pieces of gum, for instance, it doesn't matter which 2 sticks of gum I grab of the 10. So this is where order doesn't matter. So this is where this is a combination. So what I want to do is that I want to say, okay, you got 2 different things going on. We got mints, and then we've got gum. And let's label this. So we'll say mints, and then we'll say gum. Alright, so for our mints, we've got 8 mints, and what we want to know what's the probability of grabbing 1. So we're going to say from 8, we want to choose 1, or pick 1. And then concerning the gum, there's 10 pieces of gum. We don't want all 10, we just want 2. So from 10, we want 2. And then we want to look at probability is always, what you want out of the total. So what we want is 1 of those 8 mints, and we want 2 of those 10 pieces of gum. So that's what we want. So the total would represent the total of items that are in there. So we're going to want a total of 3 items, right? 1 mint and 2 pieces of gum. And that's out of the 18 items that are in there. So you notice that these two numbers, 8 plus 10 gives you 18, 1 plus 2 gives you 3. Alright, so now this is where you could see why we would want to maybe use a calculator for some of this work, if that was an option, because see, I could just put all these numbers into the calculator and skip a lot of work. But we need to be able to do this by hand, so let's show how we'd crank that out. So remember, the total goes on top. What you pick, what you don't pick. So 8 mints, I just want 1 of them, so there's 7 I don't pick. For the gum, 10 pieces, only want 2, so that means there's 8 that I don't want. And then for the total, 18 total pieces of candy in the bag, but I'm only picking 3 of those. So that means there's 15 that don't get picked. Now, I know initially, maybe this looks like a lot, but what we can do is we'll simplify this so it won't look as scary here. So 8 factorial just means 8 times 7, but you look at the bottom, you stop there. So 7 factorial, so those will cancel each other out. And 1 factorial, by the way, is just 1. And then for the other fraction, again, this is, make sure we just got this labeled here, right? These are our mints. This is still our mints, and then we're talking about gum. And I guess a third thing we could have labeled down here is total, right? Because that represents the total. All right, so let's talk about the gum then. So 10, I see an 8 down there, so that means I can stop with the 8. And then I see a 2 factorial. Alright, well let me do some canceling here. So I can cancel, like we said, we canceled the 7s there. Let's cancel the 8s. 2 goes into 10 5 times. And so what we'd be left with, at least on the top, is 8 times 45. Right, maybe we'll highlight what was left over there. So I had an 8 left over and a 5 times a 9. Now for the bottom, clear this out of the way. So for the bottom, not as bad as you might think. So you've got 18 times 17 times 16 times 15. So we'll stop at 15. And then let's look at the 3 factorial. So that would be 3 times 2 times 1. Let's do our canceling. So we can cancel the 15s. 3 goes into 18 6 times. And then 2 goes into 16 8 times. And then if we multiply that out, we can use calculator help us here. So 6 times, let's say 6 times 17 times 8, we get 816. So 816. Alright, now, so we've got to multiply this out. So this is where I guess the fraction gets a little messy. So let me come down here. So 8 times 45, if you multiply that out, you get 360. And over 816. Now, so that's a really large fraction. And one thing that you can do is that if you're not sure how to reduce a fraction is, if it's even, which this fraction is, then you can just start by dividing it, kind of cutting it in half. So if you're not sure with what to do with 360, just cut it in half. Right? And then you can cut it in half again. Oh, actually, let's try that again. 360 divided by 2, which is 180. And then let's divide that in half. So we get 90. And we can divide that in half, and we get 45. So, and then what we did is we cut it in half 3 times. So this would be equal to, let's just kind of bring this down a little bit here, 45. And if you cut 816, so we cut it in half 3 times. So you do the same thing with 816. So if you said 816 divided by 2, 816 divided by 2, and then divide that by 2 again, and then divide that by 2 one more time, we get 102. So the final fraction there would be 405 over 102. And if we wanted to express that in terms of a percent, we could put that as a percent, so we could say 45 divided by 102, just out of curiosity. So a little less than half, right? So approximately 44%. Approximately 44%. All right. So go ahead and pause now and try 7.2 and 7.3. All right. So let's check in on you. 7.2 should have got 45 over 91, so it's roughly a 49% chance. And then for 7.3, should have got 3 over 7, which again works out to roughly about a 43% chance. All right, so let's look at 8.1. Almost there, so 3 problems left. So this says, on a certain day, the chance of rain is 70% in Ventura and 20% in LA. What is the probability that it will not, keyword there is not, probability it will not rain in either city? Well, so we've got to figure out, and I think maybe an easier way to do this is to come up with a table. I think this will make a little more sense. So it's either going to rain or it's not going to rain. So we'll just say rain, not rain. And we're comparing Ventura to LA. So what it says is there's a 70% chance that it'll rain in Ventura and a 20% chance it'll rain in LA. All right, well, so the thing is that percent is always out of 100. So what that means is that if there's a 70% chance it will rain, but we're looking for the chance, and I've already boxed it, but let's highlight it as well because we really want to make sure we're clear that they're saying not. So the chance that it's not going to rain would be 30%, right? Because these two things would need to add up to 100. Well, if there's a 20% chance it will rain in LA, that means there's an 80% chance it won't rain. So the probability, and the way I'll write this, so we'll say probability of not Ventura, just kind of abbreviating here a little bit, and the probability of it not raining in LA, well, we just have to multiply those two things together. So the probability of it not raining in Ventura is 30%, and the probability of it not raining in LA is 80%. Right, so we just need to now, making a mess here, just need to multiply these two things together. And the only difference with this problem is two things. One, that they give this to you in percentages instead of fractions, right? Everything we've been working with so far has been fractions. The other thing is that they're not asking for the probability that something will happen. They're asking for the probability that something won't happen. Well, so how do you multiply those two things together? You know, maybe go to the side, just do a little scratch work. You want to convert those into decimals, right? Slide it over two spaces. So that would be 0.30. This would be 0.80. So 0, 0, 0, 24. And then there's 4 decimal places there, right? 1, 2, 3, 4. So you would have to slide it over 1, 2, 3, 4. So what you end up getting there is you end up getting 0.24, which if you wanted to convert that back to a percent, you'd slide it over 2 spots and you'd get 24%. So a 24% chance that it will not rain in either city. All right, so go ahead and see what you can do with 8.2 and 8.3. All right, so let's see what you got. 8.2, so she got a 6% chance that it was not going to snow in Big Bear and Mammoth. And for 8.3, she got a 28% chance that it was not going to rain in either Camarillo or San Francisco. Again, if you got stuck on either one of those, pause it, figure it out, ask me. If not, we shall move on. All right, number 9. So it says, draw a distribution curve representing the ages at which a group of people got married. All right, so we talked about that this is what we refer to as the normal distribution curve. Sometimes you hear it referred to as the bell curve. And what this does is that it shows you, it's a graphical representation of a distribution of data. And what I mean by that is that it shows you in the form of a picture where the average is, right? You kind of think the average is being the middle, and then of course there's always some that are above the average and some that are below the average, but that's a smaller number. So what I'm going to do is I'm just going to start by drawing a distribution curve. So the way this thing looks, it's kind of, there's a hump in the middle and then it kind of comes back down like that. And I'm going to look at the information that's given to me in the problem. So it says the average age that a group of people got married was at 25. So I'm going to label this. The middle of the curve is always the average. So this would be 25, or the mean. The symbol that we use for that, for the sample mean, would be x bar. And then they use this word standard deviation. So what standard deviation does is that it's a measure of how far most, not all, but how far most numbers are from the average. So what this means is that, okay, so if you have a group of people, the average age was 25, well, that doesn't mean everybody got married at 25. Some people got married younger, some people got married older. But most of them got married around 25. Well, what we want to do is the standard deviation tells us what the around means. I mean, is it between, 23, 24, and 25, or 22 and 26, right? So that's what we're trying to figure out. So the standard deviation kind of tells you the jump. So what it tells you is that if the standard deviation is 5, then what we're going to do is that means, it's kind of, think of it as almost kind of as a plus or minus. So what it means is that most people got married between 20 and 30. And again, where I got those numbers from is I took the 5 that was given to me there, and I added 5 to get to 30, and I subtracted 5. Right, so it sets the range of where most people are. And so this would be 1 standard deviation to the left. This would be 1 standard deviation to the right. And then so what the question is asking is it's asking how many people, what percentage of people got married in between 20 and 30? Well, between 20 and 30, that represents this entire area in between the middle part of the curve. Now, did everybody get married in between 20 and 30? Well, no. I mean, there's some people that got married older than 30. There's some people who got married younger than 20. But what you notice is that this part of the curve is more narrow. It's skinnier, because that means there's not as many people that got married younger than 20, not as many people that got married after 30. So the thickest part of the curve is where most people are at. Now, what percentage? Well, this distribution curve tells us what percentage. And so if you look at it, one standard deviation away from the average, which is this area right here, always represents 68% of whatever it is that you're talking about. These numbers don't change, right? The problem will change, but those numbers don't change. So what that says is that one standard deviation away from the average represents 68%. Right, 34 and 34, which would make 68%. So this area right here represents 68%. So that means that 68% of people got married between the ages of 20 and 30. Not all of them, right, but 68%. A large chunk of them did. All right, so what I want you to do on this problem is I want you to do the same thing I did. Draw the curve and then kind of shade in the area that they're referring to on the problem. All right, so go ahead and pause now and try 9.2 and 9.3. All right, so let's see what you got there. For 9.2, you should have got 13.5% because what you were looking for, and I'll just kind of shade it in a little bit for you. What you were looking for is actually this section right there, because the average was 5.4. 3 more inches would be 5.7. 3 more would be 5.10. So you wanted to know between 5.7 and 5.10, so that would be 13.5%. And on 9.3, should have got 34%. The average on this was 80, so 80 was the middle, and it's then a standard deviation of 10. So this would be 70, and so it's saying what percentage people scored between 70 and 80. Well, it's that area right there, so that would be 70%, or I'm sorry, 34%. 34%. All right. Hey, we made it. Last problem. Proud of you for hanging in there. The last problem that we're going to look at is actually calculating standard deviation. On that previous problem, the standard deviation was given to us, but we have to be able to actually calculate that ourselves. So that's what we're going to do in this last problem. Well, so where this whole thing starts, first of all, you have to know what the average is, right? Like you have to know what the middle is. So before you say how it kind of spreads out to either side, you got to know what the middle is. Well, the middle is represented by the mean, which is just another way of saying the average. So you know how to find the average. You just take, and again, the average we're abbreviating here just with X bars instead of having to write out the word. So you know, you just take the numbers that are there, and then you add them up, and then you divide by how many numbers there are. So there's 1, 2, 3, 4, 5. So I will divide by 5. All right, so we'll use a calculator for this. Let me get my calculator back out. So I'm going to do 28 plus 24 plus 36 plus 18 plus 30. So 136, and then we're going to divide by 5, so we get 27.2. And what I'm going to do on this, I'm actually going to do a little rounding just to make the math a little bit easier here for us. So it's equal to 27.2, but I'm going to round to the nearest whole number, which would be 27. So on these next two problems, what I want you to do is that if you get an average that has a decimal in it, just round to the nearest whole number. All right, now, so we found out what the average is. So we found out what the middle is. So if I wanted to label my distribution curve down here on the far right, So the average there is 27 points per game. Now what I then want to figure out is, okay, well, not every game he scored 27. I mean, most of these games it was pretty close to 27, 28, 24. You know, but then there's one game where he scored way above the average at 36, and then one game where he scored way below his average at 18. So what I want to do is I want to compare each one of these numbers to the average. So for instance, 28 is 1 away from the average of 27. 24 is 3 away from the average of 27. 36 is 9 away. So all I'm doing is I'm finding the difference between each number here and comparing it to the average. And it doesn't matter if the number's above the average, below the average. I'm just saying how far away. Think of it in terms of distance. So let's see, where do we left? We got 1, 2, 3. So the fourth number is 18. Now, so that ends up being 9 away from the average, and 30 is 3 away from the average. Now, what we're going to do is we're going to find an average. We're going to find an average of the differences, right? So again, there's 5 numbers. Now, the way this thing works is that we have to end up squaring each one of these numbers and then taking the square root. Right? The squaring comes in because the numbers, as I said, don't pay attention to the fact whether it's above the average or below the average. Technically, if it was you know, below the average, then we're going to have a negative number, but you can't take the square root of a negative number, so we square it out to make it a positive number, and then we're taking the square root of the whole thing to kind of back that out. Alright, so if you put all that into the calculator, and the way I would tell you to do that is maybe start by, you know, say 1 squared, you know, but I would even do this mentally. You know what 1 squared is? It's just 1, right? So say 1 plus 3 squared, which is 9, plus 9 squared, which is 81, plus 9 squared, which is also 81. I think you can do that mentally. And then plus 3 squared, which is 9. And then we're going to divide all of that by 5. And so we get 36.2. So what we then need to do is take the square root of 36.2, and we end up with 6.01, which if we were going to round that to the nearest whole number, I mean, we could say there's two things we could say. We could say 6.01. The question actually on the test wants you to round it to the nearest tenth, which would be 6.0, but we could just leave it like that. We could say 6.01. Right? So what that means is that think of it as the spread of his points per game is plus or minus 6. So like most of his points, he either scored between 6 more than his average, which would be 33, or 6 less than his average, which would be 21. So take a look at and again, I think this will really help you make sense of all this. So what it means is that most of the time he scored between 21 and 33 points. Most of the time. Now, not all the time, because there was one night that he scored above his average, 36. One night he scored below 18. So again, this represents one standard deviation will tell you where most everything is. Not everything, but most everything. All right, so go ahead and try 10.2 and 10.3. We're almost home. All right, so let's see what you got there. 10.2, you should have got an average of, when you did it on the calculator, you look at 15.7. So round it to 16. And then if you do that, then you'll get a standard deviation of 3.7. And then on 10.3, actually this one worked out real nice and clean. There was no decimals on it. I don't necessarily plan for that, but hey, it worked out. So the average is actually 75, exactly, no decimal. And then the standard deviation on that would be 5. No decimal on that one either. All right, well, that brings us to the conclusion. Really appreciate you hanging in there. Good work today. I know it might seem like a lot, but it's going to be worth it when you see your grade go up. So we'll go ahead and stop the video here, and hopefully you feel a lot more prepared and ready to take this retake test and do well on it. So again, thanks for your time, and we'll see you next time.